Welcome to the Edelman competition presentations. We have a fantastic day of 6 of the very best presentations on work in operations research and analytics. Just a few announcements to make before we get started. I'm Michael Trick. I am the chair of the judging panel. A few things. This is all being recorded and will be made available after the competition. Therefore, please turn off your phones unless you'd like it all stored for posterity. Try to not move around very much if you possibly can avoid so. If you leave the room, you will not be allowed back in, and so please plan accordingly. Please do not do your own videos of this. We've got some professional people at the back who will be providing a much higher quality product. So we are now ready to begin. In order to avoid the long introductions, I will simply introduce the teams by the company. First up is IBM.
So good morning. My name is Sandy Carter, and I'm IBM's General Manager of the Cloud Ecosystem and Developers. And the IBM team and I would like to thank you for this opportunity to share our story of how we support major golf and tennis events like the Masters, you may have seen this weekend, around the world by applying operations research to cloud computing services. This is what we call predictive cloud computing. So let's get started by taking a look at the evolution of cloud computing and why at its core it's the core of the digital revolution that's changing how we interact with each other, with business, and with other technology. Now, if we use as an example the 30-year relationship between IBM and the French Open tennis tournament, we see that in the mid-'80s, the requirement for data was really limited to statistics and scoring, and that was consumed by a very small population, mostly the players, the tournament venue, and the media. But each year since has brought more innovation, allowing more types of data to be captured and made available to many more people. In fact, they say that content is king. We say that content is the kingdom. Now, we've all experienced the rapid changes that have been brought on by this affordability and availability of the internet services. And it really does seem like overnight that content that was once available through TV and radio is now available to anyone with an internet connection. Data that really only a few privileged had available is now available anywhere to anyone. And the result is that the fans of these events can access that same data that the players, the coaches, the umpires, and the media could access before, but now in near real time. So the number of fans has really continued to grow from 1998 to 2008, about a decade, and with it, a number of mobile computing devices, such as smartphones and tablets. And these mobile platforms have really changed the compute requirement, driving that always-on environment, rapid growth of data, both in velocity, variety, visualization. And as we go forward, this places a greater demand on this compute environment to provide that data. So now we're not only running a cloud platform that's capable of supporting known demands of the connected world, but since 2012, we've been using predictive cloud computing to predict and plan for unknown demands as well. We've just recently invested, as IBM, $3 billion in a new Internet of Things division, which creates a large portion of new data demands as well. And there are 26 billion sensors in this new world. And it's this type of new data that demands a predictive technology environment. So today, if you look at it, we host a number of IBM-sponsored events from golf to tennis and even the Tony Awards on a platform that uses this predictive cloud technology. Now, not only is it for these special events, but for clients, this provides the digital experience that includes website content, scoring, live video, recorded video, and much more. Now, these events, they run year-round, and as you can see from the 2015 schedule, there are some of those that cause an overlap. which also increases anticipated consumption of those cloud resources. And we can now predict those and prepare well ahead of time. So let's just take a look at some of those 2014 volumes that users around the world are consuming. So we have over 2 billion page views, 10 million live scoring updates, and that's across 16 different digital platforms. Anticipating this real-time impact on computing resources is the difficult challenge. Now, the excitement, though, of a sporting event are the same unknowns. They're dynamic because no one knows what's going to happen next. And that is precisely what draws fans and casual observers to the event experience because it's not scripted. But not knowing what can happen day to day or hour to hour is also what threatens the availability of those same cloud resources that we provide for all those sponsored events. So having the ability to predict what may happen gives us an advantage. And that is precisely the value of this predictive cloud computing solution for our cloud platform. So now what I'd like to do is to introduce Herbie Para and Brendan Franklin, who will further explain both the problem and the challenge. Herbie?
Thank you. Thank you, Sandy. I'm Herbie Para. I'm responsible for the vision and strategy of our always-on cloud platform that we use to deliver these dynamic experiences. I'll discuss many clouds, what they do today, what inspired us to innovate and overcome the shortcomings that they have, and introduce the differences and the significant edge we achieved through our predictive cloud computing solution. The cloud, as many know, is computing as a service over the internet and even in private enterprises. It's different from the distributed systems in the past as it enables the delivery of computing resources on a pay-for-use basis, rather than having to procure, install, and configure systems in a dedicated data center well in advance of the demand. The compute-on-demand and usage-based billing of the cloud enables businesses to optimize their costs by using only what they need when they need it. This expansion and contraction of cloud resources is often referred to as elasticity. Well-controlled elasticity is what maximizes efficiency and reduces costs. Traditional methods of controlling elasticity in the cloud are based on operational analytics, what we know about the systems, or what has been learned from historical data. For example, historical data for an online retailer may help predict that Monday after Thanksgiving in the States, known as Cyber Monday, will be the busiest online demand day, and therefore we should allocate many more systems on the cloud to handle the work. If the predictions are low, operational analytics will indicate the systems are busier than expected and reactively start the provisioning of more cloud resources. Operational analytics will also indicate when the systems are not busy, and we can free up resources to save costs. In our sporting workloads, our historical analytics let us know that during tournament time, we will need 50 times the compute capacity, and our operational analytics will reactively adjust the cloud based on real-time data. So why isn't that good enough? We need a 20-minute advantage because of many things. But to summarize, the short-term analytics iterative time, which we control, and the time required to make more cloud capacity, which is out of our control. Vivek Ranadive, hope I said that right, makes the case that what made Wayne Gretzky great was not his skill as a player, but his ability to predict where the puck was going. In hockey, he only needed a 2-second advantage to be exceptional. We needed a 20-minute advantage. We need a 20-minute advantage because we want to be ahead of the demand driven by real-time events during the tournament that we previously could not predict. These real-time events, like a player injury, a rain delay, an underdog beating a top-ranked player, or some other interesting tournament event, may drive demand above and beyond our long-term analytic predictions. If the demand is above our predictions, we could fail. We needed a way to have our short-term analytics adjust the predictions based on real-time, unpredictable human events, including social media buzz, which may drive users to come to the cloud and consume more than expected. Making cloud capacity is just like building it in a traditional data center, but faster due to automation. We still need our analytics engine to initiate the build request action. Then our cloud management system will create the virtual machines and install the operating system, create the file systems, configure the operating systems, deploy and configure systems management tools and agents, install and license the software, synchronize files so they look and act exactly like other systems configured, and test the software. open the firewalls to allow specific services, perform security health checks and compliance verification, check in the assets, enable monitoring, and finally add the systems to the server load balancers so they're now part of the cloud. This is a simple summary of the nearly 300 tasks actually performed to create a new system in the cloud. And since we run out of a minimum of 3 clouds, so it's always on, we have to build and adjust cloud capacity in at least 3 places at nearly the same time. If we need to add one system, we need to add that one system to all of our clouds so they grow or shrink equally. In January of 2012, the Australian Open Djokovic versus Nadal finals match was our eye-opener and inspiration for this predictive cloud solution. When the media started sharing the record-breaking finals match on the very popular social media platform Twitter, their tweets were retweeted by fans around the world. Asia, Africa, and Europe were awake, and the Americas were waking up, and nobody wanted to miss the excitement. And they came to the cloud in large, unexpected numbers. This is when we knew we had to go beyond reactive response and use real-time analytics to predict unpredictable human events and responses. Here's Brandon Frankel to explain more.
Hi, I'm Brandon Frankel, and I was the intern focusing on the business need and advantages of our predictive cloud computing solution. As Herbie mentioned, it is all about predicting where the pucks might land, or in our case, the necessary bandwidth to satisfy demand without wasting resources. But we had a problem. We lived in a reactive world. In order to become proactive, we tackled 4 areas with new, innovative ideas to help us revolutionize the way decision-making is being conducted through cloud computing. I'd like to highlight those 4 situations today. So first, the unpredictable. Second, a novel simulator that could operate without historical data. Third, using social media data. And fourth, predicting and adjusting in real time. The unpredictable, what we can't control. There is a reason the quote, "why we play the game," is used so often in sports. For each swing, serve, or set, you don't know what is exactly going to happen next. And in some ways, social media is even more unpredictable. We never know what is the next to trend on Twitter or picked up from the TV broadcasts and amplified over the web. Along with weather, there are many unpredictable cases. In order to combat this unpredictability, we used novel numerical analysis techniques to recognize patterns and produce forecasts. These techniques produce forecasts that chose and adjusted the weight of importance to each specific algorithm that we use. These techniques choose which tool to use and how to best balance the usage of the data sources such as scores, weather, and social media. Overall, this method determines for the cloud what analytics to utilize and ensures that the operational decisions are optimized. Next, the simulator. New players, matchups, courses, and sports first, such as the longest match or playing on a unique date or day of the week, occur all the time in tennis and golf. How often do we hear, only in sports could this happen? In order to adjust to this situation, we built a simulator that is able to work with a variety of data states. Often there are quality data sets such as start times, but in these sports, the second match or the remaining players adjust their start times based on the group playing prior to them. Using big data, our unique simulator is able to work with poor quality or incomplete data to provide a solid predictive model. Next is using social media data. By taking advantage of what the social media world is saying, we are better able to predict and manage cloud resources. We do this by extracting features from tweets and correlating them with other data to predict the future. An example of this is to use data from the websites, such as hits per player's profile, and blend that with player popularity, tournament data, and social media data. The auto correlation that we created is uniquely processed with the ever-changing volume, velocity, variety, and veracity of data. This allows for properly predicting the potential for a playoff, extra rounds, or longer matches. Next is adjusting in real time. The key to our success was being able to predict and adjust our forecasts in real time. The combination of short-term, medium-term, long-term, and our predictive model capability allows us to look out hours in advance for capacity and additionally creates a highly accurate model for the next 30 to 90 minutes. In order to adjust in real time, we used a mixture of experts for forecasting, including an ensemble of cyclical forecasting that includes a vector forecaster, a half-life ensemble to merge forecasts together, a cohort forecaster that combines cyclical and event-based predictive models, and we used sliding parabolic windowing to create the cohort combination of different models. Erin and Clay will be diving into those details in a few minutes. These models are able to combine, learn, and decide which variables have more influence in each situation, and then adjust, giving more weight to variables that have a larger importance in that specific situation. These four innovations are able to add substantial benefits beyond what are typically seen in elastic and scalable cloud models. As seen in the graph, the amount of unused bandwidth between the server capacity and the server load is much less with the proactive model compared to our original reactive model. Specific benefits include 100% availability of the websites, cost savings due to less waste of unused cloud resources, and thirdly, less human and computing resources are required to run this service. Along with these advantages comes risks, which must be mitigated. If incorrect data is used or an algorithm is not tuned correctly, there's a chance of a wrong prediction, which could lead to an outage on the site or large bandwidth unused. Lastly, through social media, a sporting event could become intertwined with other news, causing an unforeseen spike in attention that models had not seen coming. Now, to expand on the algorithmic details, let me welcome Erin Bodmin.
Okay, great. Thank you, Brandon. I'm Erin Bodmin, and I have been responsible for the algorithms and big data within the Predictive Cloud Computing solution. I'll go ahead and take you through some of the details of the Predictive Cloud Computing system and then turn it over to my colleague, Clay. We were challenged to design a system that could interpret the enormous amounts of highly volatile big data that your average golf or tennis tournament generates, all while achieving 99.999% uptime. Our process takes data from a number of public and privately available data sources to make predictions. Changes in instantaneous player popularity are essential to predicting transient events that are correlated to website traffic. Web logs, which contain a reference to a particular web page, are paired with the respective pages where the content is searched with natural language processing for player mentions. Big data insights is used to determine the frequency that each page is accessed and by proxy the player's popularity in real time. The popularity is augmented with real-time Twitter data that is streamed to the system and analyzed for a variety of indicators such as aggregate tournament and player mentions as well as sentiment. Streaming web logs from our private cloud provides data velocity and acceleration, which becomes the ground truth data which we train our models with. During gameplay, scores, stats, schedules, players, status are streamed to the Predictive Cloud Computing system and are used to produce an n-tiered discrete event simulation to generate thousands of possible outcomes for each match or hole in real time. The Predictive Cloud Computing system implements a continuum of advanced analytics in support of operations research. We use a variety of advanced analytic algorithms that vary in their degree of complexity. Merging them provides a level of competitive advantage not available in prior art. Each analytic provides a particular investigation point to help reason about golf and tennis events. The simplest type of analytics help answer descriptive investigations such as what happened during the tournament, how many, how often, where did the sporting event occur, and what exactly is the problem in the cloud. The answers and summarizations to the aforementioned questions are displayed through real-time dashboards and web services. The next set of advanced analytics are predictive. Events are triggered within the Predictive Cloud Computing system to alert the cloud when additional resources need to be provisioned. As gameplay continues, an ensemble of forecasters analyze historical traffic trends to project future traffic. We can project or predict anomalous events during gameplay by computing the various simulated game states and extracted features through our algorithms. Finally, we briefly introduced prescriptive analytics to synthesize the results of our algorithms to efficiently manage digital sporting experiences. Optimization analytics, such as the Powell optimization, enable the predictive cloud computing system to determine how we can achieve the best resource allocation given the evidence. The combination of prescriptive, predictive, and descriptive techniques provide an overall advanced analytics system that enables operational research interfaces for both humans and the cloud. So during gameplay, we provide real-time predictions and forecast. First, traffic data from our servers is sent to the ensemble of time series forecasters, where a function determines the number of website hits per minute at a specific time. At this step, 5 forecasters with complementary time horizons are applied to produce a plurality of forecasts. Next, the forecasts are combined and smoothed during the post-processing phase. Data such as golf and tennis scores, schedules, statistics, tweets, and web content is streamed to the distributed feature extractor algorithms that run on the same technology in which Watson won Jeopardy! Simultaneously, golf and tennis events are generated by the distributed chain simulation, which is consumed by the feature extractors. All of the extracted features are predictive modeling are applied within a multiple regression model to predict anomalous events that in turn provide the expected server hits per minute to the origin server. Our training set updates daily during off hours. During training mode, the ground truth data of demand over time is merged with the exemplars extracted from the historical data repositories. Next, a residual forecaster is applied to adjust for mathematical interpolation errors. And finally, the time series forecasts are combined with a half-life algorithm and input into a sliding parabolic merger. The final forecast, including all of the forecasting components, is displayed on a real-time analytic dashboard. For players, the objective is to maximize the number of major golf or Grand Slam tournament wins. Our objective for the predictive cloud computing system is to minimize the root mean squared error measure. We accomplish this through the application of forecasting ensembles and prediction cohorts. The forecasting ensemble utilizes a novel half-life weight merger to optimize the accuracy of the forecasted server hits. A moving parabolic weight adjuster then combines the predictive modeling and forecasting ensemble into a merged cohort. As a result, parts of the advanced analytics are changed and empirically driven to increase the overall accuracy of the forecast. During each sporting tournament, a real-time predicted schedule is generated by a chain discrete event simulation algorithm that iteratively increases our tournament search space. For golf tournaments, the golf simulator has to account for split tees, shotgun starts, playoffs, player disqualifications, cut rounds, and play suspensions due to weather. The predicted schedule of play is not chained, but is a discrete event simulation. However, the predicted schedule that generates features for our event-based predictive model runs in the chained mode over distributed machines. During simulation evaluation, we found that real-world data can be very inaccurate. This caused the simulator to predict unrealistic schedules. To combat this, 3 types of discrete event simulators were developed. When gameplay data is inaccurate or not accessible, a data-independent simulator is invoked with a minimum amount of seed data, such as golf tee times. On the other extreme, a data-dependent simulator requires data such as tee times, hole schedules, scores, and tournament information. The data-dependent simulator is very accurate with respect to actual event changes, but is very computationally expensive. As a compromise, a hybrid simulator requires some data such as tee times and hole information and can predict schedules of play within real time. The demand curve for cloud resources has irregular spikes that coincide with major matches or rounds. The predictive model addresses this challenge by adding spikes to the predicted curve for short burst periods. To discover the future pattern, analytics extract features from a completed chain discrete event simulation as input into a multiple regression model. The feature extraction algorithms are categorized as social, cloud, golf, or tennis. Each of the groups of algorithms are then run as analytical pipelines within UEMA. Within the golf pipeline, a total of 6 algorithms extract features from the golf simulation. For example, the featured group predictor determines if the current group of players is likely to cause a media frenzy. The cloud pipeline includes 3 log traffic analytics over any type of sporting tournament simulation. The 3 cloud features are all related to real-time log traffic, such as the real-time log count feature that provides a summation of all streaming access logs over the most recent half hour. The social pipeline is comprised of 9 social algorithms. One example of social algorithms includes the Twitter streaming count analytic that determines the sum of tweets just before a simulation begins. The predictive power of each predictor was determined by SPSS statistics that combined semi-partial and zero-order correlation. Before each tournament, the R-squared value averaged around 0.92. Overall, the model achieved an average percentage error of 5% that ranged from 5,000 to 10,000 web server hits per minute. Methods such as bagging nor boosting improved the performance of the models. Each of the predictors are visualized with real-time predictive power bubbles, while the overall type of feature contribution is updated through a donut plot. Spark lines show the instantaneous number of completed algorithms in support of the predictive model. All of the graphs and charts change in real time. Brian O'Connell will provide more details on the user interface. Now I'd like to go ahead and turn over the talk to my colleague Clay Upton.
Thank you, Erin. As you'd expect when observing daily trends, the average appears largely sinusoidal, the variations being the peak amplitude, the phase shift marking the start of the day, and any transient events that occur throughout the day. The Predictive Cloud Computing System has a distributed and real-time forecasting system that serves as a baseline for the daily trends independent of transient spikes in traffic. This forecasting system operates by splitting up weeks of historical data into individual days. The software then aligns the daily curves by relaxing the amplitude and the start time using Powell optimization algorithm. These curves become the training data that we employ for a variety of forecasters. Because this data might have time gaps due to human, system, data format errors, an imputer merges the currently available data with the best guess based on historical curves. Once trained, an ensemble of time series forecasters predict the long, mid, and short-term ranges, and these forecasters are merged using normalized half-life weights and serve as the baseline on which traffic spikes are superimposed. The vector forecast is very powerful. It is capable of predicting gross trends 8 hours into the future by numerically integrating current traffic over the vector field consisting of the second-order derivatives of all training data. It uses RK4. The quadratic and cubic forecasters utilize the Gauss-Newton algorithm to regress and forecast 2 hours into the future to anneal the effects of the vector forecaster. All the forecasters implement Loess interpolation for advanced smoothing. During the 2013 U.S. Open, the men's final match was moved to an unprecedented Monday evening. We did not have the training data to teach our time series forecasters that pattern. So to discover the anomalous pattern, multiple regression event-based model was applied. Looking at the graph, if the time series forecasters were used exclusively, then the traffic spike toward the end of the day would have been missed. However, when the event-based predictive forecasts were used, the traffic predictions at the start and end of the day would have been too low. The combination of time series and event-based forecasting model enable the Predictive Cloud Computing System to accurately predict the future. When both forecasting types are joined into a cohort, the mean average percent error is reduced by 8.19%, while the RMSE improves by 9,615 hits per minute. During the major golf tournaments and Grand Slam tennis events, servers are automatically provisioned based on the forecasted demand from an ensemble of forecasters. For each minute of the forecast, the number of servers to provision is calculated. The graph depicts a real-time visualization of the Predictive Cloud Computing forecast. The goal is to match server capacity with demand, all while maintaining 99.999% uptime. Thus, we must never allow the demand to exceed the capacity of the cloud, because doing so would result in end users receiving resource errors and an inability to access portions of the sporting website. The closer we look at match demand, the more computing resources we can save. Working with these constraints, we're able to save 51% of the computing hours, or 134.5 hours per typical match day. Now I'd like to turn it over to my colleague, Brian O'Connell.
Thank you, Clay and Erin, for providing the mathematical details that explain how Predictive Cloud works. I am Brian O'Connell, a senior technical staff member at IBM, and for me, I have found the best way to really understand the impact of this technology is to look at it in action. What you're looking at here is a snapshot in time from the 2014 U.S. Open. This is midday, the second week of the tournament. You've heard the details of the methods and technology used to power our predictive cloud so that it can respond to future demand. The technology is exciting, but what drives people to our platform is the unique content created by our partners. The most important content from a cloud load perspective is people playing tennis. Right now, let's focus on the top part of the visual. We'll come back to the forecast and instance time saved later. At the top is the forecasted schedule from our analytics software. Our system ingests data from the tournament office and IBM systems to predict when matches will start and end. Additionally, the analytics software looks at outside factors like weather events, including rain, that can cause a delay and shift the schedule. We use this predicted schedule to figure out when we're going to get peaks in traffic to our cloud. Now we just have to figure out how much traffic that is going to be. The first thing we do is we look outside of our cloud and we ingest data from Twitter. We use Twitter to detect instantaneous changes in player popularity. In other words, history tells us that we think Djokovic should be responsible for about 80 tweets per minute. If all of a sudden Djokovic is mentioned 800 tweets per minute, something has happened around Djokovic. We don't know exactly what it is, but we do know that it will drive people to the digital platform, increasing traffic to our cloud. We also use IBM Analytics technologies to analyze in real time all Twitter messages relating to the tournament. Measuring this general social media activity and detecting when it differs from historical numbers lets us predict when our cloud may need to grow to handle something extraordinary going on at a sporting event. Now, one of the things that makes a tournament such as the US Open so exciting is that anyone can win. However, not all players will impact our cloud in the same way. We're using IBM Big Insights, built on top of open source Hadoop technology, to figure out the most impactful players. Every few minutes, we perform unstructured text analytics across the content of the website. In plain English, we figure out if at a point in time a web page is talking about Serena Williams, Roger Federer, or the menu at the Aces restaurant at the US Open. We then look at every single hit to the website to figure out the relative interest of our fans for each player at this point in time, because that will drive resource when they're playing. The graph you're looking at here is a summary of those two types of player impact, the social and the player views. So that first visual we looked at told us when to expect certain spikes to our cloud. This one tells us how big they're going to be, which in turn tells us how many cloud resources that we need. I just finished touching on some of our log analytics work when discussing our player impact system. However, there is more to it than that. What you see on this screen is the visualization of a day's log analytics for US Open. In addition to the player view analysis I talked about, we also use Big Insights to feed our learning algorithms. This lets our system learn from previous and current US Open tournaments to generate highly accurate forecasts. Also, if you look in the upper right-hand corner, you can see our real-time logs. We use this to automatically check how close our forecasts are to reality. If they're diverging, the system uses smarter analytics to automatically adjust and help reforecast for the day. Clay and Erin took you through the algorithms that have been developed to make Predictive Cloud so accurate. What we're showing here at this snapshot in time is the relative impact of the different algorithmic factors into the prediction. As the tournament progresses, the different algorithms, depending on what is happening on the social or tennis world, can shift in importance. This screen helps us see which elements are impacting our prediction the most. We use this section of our visual to pinpoint in time where various Watson technologies, like UEMA, have influenced our predictions. The section in red is a specific location in time where the Watson Foundation technologies influence the prediction significantly. Without this technology, the system may have underpredicted traffic at that point in time. This is the most recent element we've added to our system. We call it Twitter Reach. We have started to explore and incorporate into our predictions a calculated score of all tweets we analyze. For example, a tweet from ESPN about the US Open may reach more followers and impact our cloud more than a tweet by a relative unknown. This section shows how that reach has trended over time for both player-related and tournament tweets. Going back to the first visual, you can see the output of the Predictive Cloud technology at the bottom of the visual. The yellow line is our traffic prediction, the purple line is the traffic we have received so far, and the blue line is the capacity allocated on our cloud to handle that prediction. The gray that runs along the top indicates our previous static allocation strategy before Predictive Cloud, and the blue line is our savings. On the left-hand side, you can see the cloud instance time we have saved so far for that particular day. It's only 5 p.m., and we have saved almost 3 days of compute time. I hope this visual has helped demystify the complexity and shown the potential for predictive cloud computing. I now welcome back Sandy Carter. Thank you.
Well, thank you, Brian. So what Brian just showed you was the example of how the predictive cloud computing system from one of these sponsored tournaments, that same dashboard that you saw, has been used for over 17,000 clients from our technology and innovation tours. We've also had magnificent coverage with press interviews and media, as well as in industry and cloud conferences. All of those have been very positive. And the results of this work, we've also filed 16 patents, and we're expanding conversations with our clients who are now very interested in this transformation. So sharing this experience of innovation and the art of the possible really draws new clients into IBM. Now, as Brian illustrated, after several years of design, development, piloting, and tuning, we now have this production system in place to support all of the IBM-sponsored events. So let's look at some of the results from 2014. In 2014, we're able to confirm in compute consumption, we were able to reduce that compute consumption by 51%. That meant we saved 44,000 compute hours, or $2.2 million over the yearly IBM-sponsored tournament season. Projecting over a 20-year period, our patent attorneys also estimate that $80 million of license value across those 16 patents that we filed. But for us, improved overall customer satisfaction is our number one result, and that is by leveraging this predictive cloud to drive future IBM cloud revenue. In fact, if you look at 20 and 14, we saw an explosion in cloud based on opportunities that were brought in to IBM from viewing the power of this solution. We grew our cloud revenue for IBM an impressive 60%, and our mobile revenue by more than 200%. So you really saw how predictive cloud computing helped us to manage these dynamic shift changes in traffic patterns and the unknowns that come with a live sporting event. However, that's just one application. As you can see from this slide, this predictive cloud computing solution has applicability beyond those sporting events. So think about it. Whether it's an insurance company who does see increases based on weather, or a retailer who has unpredictable items, or a city. For instance, think about inclement weather for things like Hurricane Irene, or even our recent win with the weather company, whose solution helps solve real-world problems that face companies today. So this IBM solution is truly innovative, and it's differentiated from anything that's offered in the industry, not just for these sporting events, but beyond to these enterprise clients. The future advancement of the predictive cloud computing is imminent. First of all, what you saw was it was smart. It leveraged machine-based learning to drive predictive, not only into sporting events, but into the enterprise. It is predictive with the vast amounts of data that are coming in from Internet of Things, mobile devices, and refined with unmatched analytics. It is adaptable, and you see that it's unique because we filed 16 patents to enable this as a first of the kind for the cloud. And it's always on. It's constantly focused on that impeccable client experience. So with that, we'd like to thank you for your time, and we'd like to take any questions.
Thank you.